module. Let me tell you the background. The background of this module is that so far we have learned. Can everybody see the slides? They can hear me. They can see me.
Yes, sir.
Yes,
Good.
sir.
So basically, the background is that see, we have actually studied chemistry of crude oil. We studied what are the various hydrocarbons which are present, how and what are the utilities of those hydrocarbons, whether in particular streams they are good news, in some streams they are bad news, and how the industry and the refining industry really looks at them in terms of making the finished products that you and I use on a daily basis. Not only that, we also talked about various impurities which are present, and then later on in the module 2 we talked about since actually it's a very complex mixture, there's no way we can analyze it. So we came up, the industry came up with some broad, what I should say, broad properties, which actually using which we try to understand crude oil. One of them, of course, is where it came from. Number two, in terms of what is the density, so how heavy, so EPI gravity tells us whether it's a light crude or a heavy crude. And then, of course, Watson K or UOPK tells us whether it is paraffinic, naphthenic, or aromatic. And that way, we actually try to define the crude and understand the crude. And then we have various other physical properties like distillation, CCR, etc., by which we try to characterize the crude. Now, actually, what happens is that there is some, there is some silver lining in this black cloud in the sense that although crude oil or hydrocarbons coming out of crude oil, whether it is gasoline, whether it is kerosene, whether it is diesel, or even vacuum gas oils, which are actually the products from a vacuum distillation, they actually are complex mixtures, but they do actually follow a certain rule. And the good news is that if we know two physical properties of any particular hydrocarbon mixture, for example, if I know density, if I know UOPK, more or less, I can actually derive other properties as well. And although they may not be that accurate in terms of the actual values, but they are fairly good. And all these commercial simulators that you might have used in the past, like for example Aspen or HISIS, HISIM, etc., they have all these inbuilt correlations in them, these industry correlations, which actually relate any physical property of that particular stream with the minimum two properties. So basically, you need at least two physical properties, or maybe more, maybe two or three, to actually define or understand or actually derive a certain physical property. And this particular module today is going to actually, discuss this very important set of tools which we have developed in the refining industry over the last 1 century. And these tools are very important in the hands of a refining engineer. We use it actually almost on a daily basis. And if you're simulating, let's say, a distillation column, which is distilling hydrocarbon mixtures, then this software, which I mentioned earlier, Aspen or HISIS, they actually give you physical properties of those hydrocarbons based on these correlations itself. Okay, so today, what we will learn is, how do we convert? Suppose we don't have to do TBP. So last module you that true boiling point distillation is actually the real data of that particular mixture. But if suppose we don't have time for that, and it takes almost a day. So if we can run within half an hour a D86, then how do I actually derive TBP from D86? So we talk about that. And suppose if I have a GC using which I can do D287, then how do I convert that to TBP? And actually, if you ask me, any petroleum fraction, including the crude oil, doesn't boil at a single temperature like water, which boils at 100 degrees Celsius at atmospheric pressure. You got benzene, which boils at 80.1 at atmospheric pressure. And at different pressures, you have equations like Antoine equation or Clausius-Clapeyron equation. So you must have studied all this in your thermodynamics in undergraduate classes. So, but this is not applicable here because it starts boiling at a certain temperature and completes, and then complete vaporization happens at another temperature. So, when we need, let's say, the average boiling point to be used to calculate Watson K or UOPK, remember UOPK is cube root of average boiling point in degrees Rankine upon density. So, which value do we use? I mean, so we defined the various kinds of boiling points, and which is the one that we typically use mostly, and then some of those definitions which I had asked you to write. So we will actually go through those definitions, and then I'll share with you these very important correlations which are called API correlations. Again, API stands for American Petroleum Institute. So there's a large amount of data which has been used to develop these correlations. And this is very, very powerful set of correlations in your hands going forward. So actually, before we begin, like to actually recap what we discussed earlier in terms of a distillation curve. And again, here, as you know, the distillation curve is boiling point in degrees Celsius versus cumulative weight percent recovered or volume percent recovered, whichever way you want to represent the x-axis. And you get a typical S-shaped curve, and basically from 0 to something like 360 is atmospheric, about 360 to something like 540, 560, 570, whichever way the distillation column is designed, we actually go up to 560 here, and above 560 is extrapolated because that you can't distill in any way. So this is actually now this distillation curve could be either TBP, it could be ASTM D2887, or it could be even D86 combined with D1160. And if you look at, if you compare the TBP and ASTM D86 on the same graph of boiling curve, this is called as a distillation curve, temperature versus volume percent vaporized, you'll find that the ASTM is data. The ASTM temperatures for the same volume percent distilled is always higher, below 50% recovery, and above 50% recovery, it is lower. The reason I had, if you remember, I had mentioned last time, is that the reason is that this fractionation that happens in a TVP that actually helps you to below 50 degree. It helps you to actually condense the less volatile components down, and only fractionating the less volatile components in their corresponding boiling point. So that is why actually you will get a TBP curve which is lower than ASTM, below 50% point, and above 50% point it is higher. So please very, very strongly remember this, that below 50% point the TBP curve temperature is lower as compared to ASTM because of this fractionation that we do, and at above 50 degree the situation is reverse, because above 50 degree, when you are actually cross the 50 degree point, then you got the heavy stuff in the bottom still. And if you got a fractionating column about 15 or 20 theoretical plates with a high reflux ratio, you are able to actually condense any vapor coming from the bottom of the still, which is of a higher boiling point. And that is why actually your curve goes up. While in this case, what happens is in ASTM that you're just vaporizing. So everything vaporizes at a certain I mean, for a certain recovery, you get a certain temperature, and it will be a kind of a representative temperature of both light ends as well as the heavy material, because there is no fractionation there. So this is actually what happens, and I'll just give you an illustration here. For example, this light FCC gasoline. I think I showed you this slide earlier also. This is how ASTM D86 is given. And so if you actually plot this ASTM D86, you get this graph. This particular graph is typical for fractions which are what we call as a hard cut. I deliberately actually tried to show you this slide. This is of course the data from one of our own streams in Reliance Jamnagar, and this it is called light FCC gasoline, and you can see that IBP of course is always low because this is the first drop which comes, but 5% is more representative of the actual boiling point. I mean the initial boiling point. So in the industry, when we look at this data, we actually concentrate more on the 5% and 95%, because after 95%, the rest of the material might take yeah, it might take a higher temperature before it boils off completely because of some residues or something remaining there. So basically, this material boils between 67.9, roughly 68 and 76. So you can see it is a very narrow boiling range material. And these kinds of material we call as a hard cut, HEART, hard cut. This is not the hard that we have, but it is, and neither it is HARD, it is HEART. So basically, we call this as a hard cut, where the spread between the 5% and the 95% is less than 10 or 15 or sometimes even 20 degrees. Okay. Generally, as you know, we've been talking about IBP of 65 and point of 210. So some of these fractions like gasoline, jet fuel, diesel, they're wide ranging, boiling range. So this is called as a hard cut. And if you plot that on a temperature versus volume percent distilled paper, you'll get a graph like this. Okay. Now let us look at how we suppose I don't have time, and or maybe the TBP apparatus is busy somewhere else, or if it is not working well, and I can do an ASTM D86. So if I have the ASTM D86, how do I convert that to TBP? So this is actually, this equation numbers, etc., are basically in the API equation numbers in the API data book. So I have actually taken a snapshot of the API data book itself. Now these are things which you will not find in the common literature. Okay, these are industry reference textbooks or industry manuals, and since we have been personally, I have been following this for the last 45 plus years. You have the advantage of actually, seeing these equations and learning them. So let me. So we actually start with 50% because, as you know, at 50%, the two temperatures are roughly equal. Okay, and the variation happens above 50% or below 50%. So what we do is the first step. I repeat, the first step to actually convert an ASTM D86 graph curve into a TBP curve is to actually get the TBP 50% boiling point. That is the boiling point at 50% recovery. If you do TBP, then what will be that value? If I know ASTM D86 50% value. So it is, and this is valid for any hydrocarbon fraction for any hydrocarbon. So TBP 50 is the true boiling point distillation at 50 volume percent distilled degrees Fahrenheit. And ASTM D8650 is observed D86 in degrees Fahrenheit. Unfortunately, we still have to work in degrees Fahrenheit. So, and then to determine the difference between adjacent cut points. So what we do now is that we have to actually estimate 10%, 20%, 30%, 40%, 60%, 70%, 80%, etc., etc. So what we do is that we use this equation where yi is equal to a into xi raised to the power b, where a and b are constants. and Xi is the observed difference in the ASTM D86 distillation temperature. I will actually, illustrate this procedure with an example later on, so it will become much more clearer to you. But Xi is just the delta between two different percentage recoveries, sorry, two different distillation temperatures between two cut points. That means, for example, if suppose 50, if you go higher than 50, so 70 minus 50. So 70 minus 50, what is the temperature for 70% recovery and what is the temperature for 50% recovery? So we take that delta T. And then delta T is plugged into this equation to get the delta T corresponding to TBP. And the A and B varies. These values will vary depending upon the cut range that we are talking about. So between 50 to 70, we have these constants. You don't have to memorize them because they are available. And actually, if suppose somebody asks you to do the calculation, these numbers, these tables will be there with you. So as for now, just remember that actually the A and B, they do vary. Actually, they keep on more or less, there is no certain equation, but you can see that the two corresponding, that is 70, 90, 50, 30, they are roughly equal, etc. And so actually, based on the delta T of the ASTM D86, we actually calculate the delta T corresponding to TBP, and then we add or subtract. Now, where do we add? Where do we subtract? Actually, as you know, so just remember that this is Y1, Y2, Y3, Y4, Y5, going from 100 to 90 up to 10 to 0. So once we get those Ys from starting from 50% onwards, when we go, when we go towards zero, we have to subtract because actually your TBP is lower than ASTM. So whatever temperature I get of ASTM, I have to subtract that delta T to get my TBP delta T. And above 50, I have to add. So this is why we do this way. So above 50, that is going from 50 to 70, I add Y3. From 50 to 90, I have to add Y3 plus Y2 because Y2 is now actually as shown here, and then Y1, which is actually what we get to get TBP 100. And vice versa, and we need to do the other way around below 50. That means this Y4 that you get here between 50 to 30, you have to subtract, and then 10 you subtract Y4 minus Y5, etc. So it is, so this is very clear. Like you first of all get, I'll just repeat the whole thing. So to begin with, you get you calculate the TBP 50% temperature. Once we know, since we know the ASTM D86 50% temperature, and then we need to calculate the delta T's for the TBP, that is 50 to 70, 70 to 90, 90 to 100, and similarly below that 50 to 30, 30 to 10, and 10 to 0. So that delta T's we calculate because we know the delta T's of D86, and those delta T's are used in this equation and the corresponding A and B depending upon which cut we are talking about. And we get this Y1 to Y6, and that Y1 to Y6 we either subtract or add depending upon if we are below 50%, we subtract. If we are above 50%, we add. Let me illustrate this with an example. So suppose we need to estimate the atmospheric TBP distillation temperature for a petroleum fraction, in which we have the experimental data for ASTM D86, which is given in the following table. So we got volume percent distilled 10, 30, 50, 70, 90, and this is ASTM D86 degrees Fahrenheit, 350, 384. Just for actually comparison's sake, I have given the TBP temperature in degree Fahrenheit also here, which is corresponding to which is actually experimentally measured data. This is experimental measured data. So the idea is to just compare, like whatever calculations we do using the previous correlations, how do they compare? How do the TBP values compare with the actual experimental data? So what do we do here is that using the equation that we talked about and the procedure that I discussed, to begin with, we actually calculate the TBP 50. And that we do by using 404, which is ASTM D86 50% point, and the same parameters 0.87180, etc. So we get TBP 50 as 411.2. This is what we predict. And the actual measurement is 409. So we are not too far away. And then actually using the delta T equations at the 30% point, that means we have to take 50 minus 30. So this is 404 minus 380. So that is actually 24. And this is 24 degree Fahrenheit. And this 24 you plug in here and you get Y4, which is 38.6. And this Y4, since we are actually below, we have to subtract. So this Y4 is subtracted from this 411.2 and you get 372.6, which is TBP 30, and which is not very far away from the actual experimental data of 371. So like that, we go further down. So basically, we go to 10 degree also, and then 30 minus 10 is 380 minus 350, which is 30. And this 30 degree, we need to then use this formula here. Um, this formula here, the 30, we need to raise 30 to the power 0.7164 and multiply that by 4.9004. And then we get a number which we have to subtract. So like that, actually, we get, Y2, Y3, Y4, Y4 we have already done, Y5. And then actually below 50, we subtract. So this TBP 10 that we got, that is from 372.6 minus 50, minus 56. That is what we actually, yeah. So this is 372.6 is the ASTM number. Just a moment. This is yeah. So here actually we subtracted 56, and then TBP 70 you have to add. Okay, so plus 40. And so on and so forth. So basically, you actually estimate all these using these correlations that I showed you. So this 372.6 is what we actually calculated here. So 372.6 minus this Y5 is what you get as TBP 10. At 70, you take this 411.2, which is TBP 50, and add 40, and then you get TBP 70, and then for TBP 90, you have to take this 451.2 and add 45.5. So this is how, and these are not too far away from, at least it is better than nothing, in terms of getting the TBP data. And this was actually programmed. These correlations were actually derived from a graph like this. In good old days, when there were no calculators, people actually had to do all hand calculations. You can see that this is actually upgraded to January 1994. It is API technical data book. And what is plotted here is TBP temperature difference, delta T TBP, which we want to calculate. And this is value which you determine by ASTM D86 or ASTM 1160, depending upon whatever, whether we are doing D86 or 1160. So whatever the delta T, let's say if it is 60 degree, from 50 to 70, you can read off. And from 10 to 30 or 30 to 50, you can read off correspondingly, and so on and so forth. So this was the kind of a nomograms which were available earlier. Similarly, the procedures remain the same, only the parameters change. So if you want to convert ASTM D287 to TBP, then basically the ASTM D287 50% point is the same as TBP. There is no difference here. But as far as the other delta T's are concerned, again, you have C and D, which is tabulated here, and V is the simulated distillation temperature difference between two cut points. So, this is what we try to do, exactly the same way as we convert D86 to TBP, similarly D287 to TBP. And exactly the same way, that means below 50, you have to subtract, above 50, you have to add. And I'm just for completeness sake, I'm sharing some of these other correlations also with you, like ASTM due to D287 to ASTM D86. And well, this is not, this is a relationship between two different methods, like converting a GC based method to D86. We don't use this very often, so this is just to actually get you all the information in one place, so that in future, if suppose you join this industry, you would have this information with you. Okay, and so this is whatever I have covered so far is extremely important for you to remember, because this is how we actually convert one distillation curve into another distillation curve. Overall, the most important is to convert a D86 or D1160 to TBP. That is the most important. And the next is the D2887 to D86, sorry, to D287 to TBP. And so this is something that we do. And believe me, these are the correlations which are actually programmed in Aspen or HISIS as well. So if you actually give ASTM D86 data to Aspen, it doesn't use ASTM D86 data for doing the actual calculations. It uses TBP data to do the actual calculations. So it actually internally converts ASTM D86 or D1160 to TBP, and the equation that it uses internally is what actually I shared with you just now. So it's very important for you to know this. Then now coming to the properties of the hydrocarbons and their relationship with distillation data, I told you that there is some there is some commonality in this madness, where such complex mixtures, but they do actually follow a certain trend, and this trend is we take advantage, so that if you know two properties, we can derive the other property. So the most important, of course, is the average boiling point, because the average boiling point describes what are we looking at. Are we looking at the crude oil? Are we looking at gasoline? If it is gasoline fraction, that is naphtha fraction. Are we looking at light naphtha, or we are looking at heavy naphtha, or are we looking at kerosene or diesel, etc., etc. So actually, having worked in this industry for 4 decades now, if suppose somebody tells me like the average boiling point of this mixture is so and so, so I roughly know like which particular hydrocarbon range would it belong to. Okay, so which particular stream does it belong to? But for us to use the average boiling point in calculation of UOPK or Watson K, we have to understand which boiling point do we use. There are five definitions of average boiling point. One is called as the volume average boiling point. The other is molar average boiling point called MABP. Then we have a weighted average boiling point called WABP. And then CABP is the cubic average boiling point. And finally, it is mean average boiling point, MEABP. Actually, the mean average boiling point is something which we use to plug into that equation for calculating UOPK or Watson K. So this is what we use. And the way these boiling points are calculated, I'll just skip this graph because these are the good old ways of doing these calculations when the calculators were not that easily available. So basically, what we do is that there are three steps that we follow. The first step is to calculate the volume average boiling point. The volume average boiling point calculation is very straightforward and simple. What we do is that we obtain that we use ASTM D86. Remember ASTM D86. And take the 10 distillation temperatures at 10%, 30%, 50%, 70%, and 90% recovery. We take these temperatures and take an average of that. So, for example, T10, T30, T50, T70 plus T90 upon 5. Uh, just to illustrate to you, like for example, the this data that we had. So if I want to calculate the volume average boiling point of this mixture, what I will do is I take the T10, T at 10% point, which is 68.4, plus 30% point, 68.9, plus 50% point, which is 69.6, plus 70% point, which is 70.8, and 90% point, which is 93.8. So 1, 2, 3, 4, 5. So I add all of them and then divide it by 5. So this actually gives me the volume average boiling point, which is VABP. That is the first one that is shown here, the volume average boiling point. And this volume average boiling point is just an average of these 5 temperatures in degrees Fahrenheit. Then what we do is we calculate the slope. That means we calculate T90 minus T10 upon 90 minus 10, which is 80. So this is the slope. So if for this data, which I just showed you, what is the slope? The slope is 73.8 minus 68.4. How much is that? 73.8 minus 68.4. So that is roughly about 5.4. So 5.4 divided by 80. Now, this is another way to define or to understand whether a fraction is a wide cut or a hard cut. So, if the hard cut if the fraction is a hard cut, then the slope will be very small. I mean, the value of the slope will be very small. Like in this case, it is 73.8 minus 68.4, which is 5.4 upon 80. But if it is a wide cut, that value will be higher. है So this is the slope, T90 minus T10 upon 90 minus 80. And now these two variables, the VABP and the slope, is used to calculate all the other boiling points that we talked about. So if suppose I want to calculate the weighted average boiling point, WABP, which is given by TW, then TW is equal to volume average boiling point plus delta 1. Okay, and delta 1 is given by this equation, which is actually a function of volume average boiling point in degrees Fahrenheit and the slope in degrees Fahrenheit. In degrees Fahrenheit. So you get delta 1, and then you add that to volume average boiling point, you get weighted average boiling point. If I want to calculate the molar average boiling point, which is given by Tm, I need to calculate delta 2, which is given here. The equations are the same, but only the constants are different. And I subtract that from the volume average boiling point, I get molar average boiling point. If I want to calculate the cubic average boiling point, that is TCU, then TCU is again given by the similar equation where we have to now use delta 3. Don't try to memorize or mug this up. You can never memorize this. It is just for you to understand that this is how actually we calculate. And this can be programmed on an Excel spreadsheet, so on and so forth. So you don't really have to actually really use a calculator to do this. And then finally, the most important boiling point, average boiling point, is of course our MEABP. So please remember, the mean average boiling point is what the industry uses, because this is a typical average boiling point that actually the hydrocarbon fraction would have. And this mean average boiling point is given by this equation, that is the volume average boiling point minus delta 4. And this delta 4 is given by this equation. So basically, if I have to calculate that, so I'm not going to actually deliberate further on the other three boiling points. That is either on the other three, like molar average boiling point, or weighted average boiling point, or cubic average boiling point. Please remember there are only two boiling points which are very important. One, of course, is the 50% point, which we actually got when we did the ASTM D86 or D1160. But using that data, that is all the entire spread from T10 to T90, I get the volume average boiling point, and then I calculate the slope. And once I calculate these two variables, I use this equation to get calculate the delta 4, and then I plug that in this equation to get my mean average boiling point. And this is the mean average boiling point that you use in your Watson K or UOPK equation to actually derive in order to derive the mean UOPK or Watson K. So I'll again repeat this. Please don't forget, because in my earlier classes, people, I mean, the students use some other boiling points which actually made them to lose their marks. So mean average boiling point is what we use in actually calculating the Watson K or UOPK in degrees Rankine, and that is derived from the volume average boiling point, which is given as an average between T10 to T90, and the slope, which is T90 minus T10 upon 80. And these two parameters are plugged into this equation to calculate delta 4, and then you subtract that from the volume average boiling point to calculate the mean average boiling point. So this is actually an example by which you can actually put all this together. So we have data here, which is ASTM D86 data for a certain fraction. And you can see that it is going from 10 to 90, that Fahrenheit is 149 to 371. So basically the volume average boiling point is nothing but the addition of these 5 upon 5, which is 271. So it is somewhere lower. It is slightly lower than the 50% point. And then the slope is 2.78. And then once I know the slope and the VABP, I plug into that equation. And the molar average boiling point, you have to subtract that by value of 30, whatever is derived from that equation. Similarly, cubic average boiling point, weighted average boiling point, you have to add, and then mean average boiling point minus 90. So you can see that the 252 is the mean average boiling point for this mixture. And if I know the density, I can actually calculate the Watson K, and that will give me an idea whether this material is paraffinic or non-paraffinic. Okay, so coming on to some properties, I do not know how much time do we have. Yeah. So this will not take much time. So this is the definition that I had asked you to search and write. So these are very important, what we call as macro properties or average properties of hydrocarbon mixtures. A flash point is actually the lowest temperature at which the application of a test flame causes the vapor of the specimen to catch fire or ignite at a certain condition. So basically, you have an apparatus in which you actually put this liquid, and the apparatus itself actually starts increasing the temperature, and the lowest temperature at which it ignites. So basically, why it is so important? The importance is because if I have some light material in that hydrocarbon, how do I know that this hydrocarbon has some light material? For example, this particular thing is extremely important. For example, the kerosene that is sold has a minimum flash point specification of 35 degrees. The reason is that if I put some gasoline rich material in kerosene and people use in the villages kerosene for cooking, and if that kerosene has some light material, then that kerosene stove can catch fire because that light material will catch fire much earlier than the kerosene, and the kerosenes can that stove can explode. And it might look hypothetical to you, but it has happened in Assam, and that is also not too far back. It is only about 10, 12 years back, where 35 ladies actually died while cooking food because the kerosene had some light material. And then I was chairing that committee to do the investigation, and we found that the kerosene had a lower flash point. It was something like 17, 18 degrees flash point. So that means there's some adulteration that has happened in that kerosene. So basically, flash point is a very important variable, and we actually specify the flash point in most of these petroleum fractions. That is the minimum flash point that we need. Pour point is the lowest temperature at which the petroleum fraction will flow or can be poured. And this can go all the way from naphtha up to vacuum gas oil and even beyond to vacuum residue. So if the vacuum residue is solid, rock solid at room temperature, we start heating it up, and if we heat it up such so that you can just pour it like a liquid. And these are all ASTM methods. They are very standardized, and it's the same material if it is done by 10 different people, by 10 different labs, by 10 different cultures. It doesn't matter. You'll get the same value. The smoke point, I think last time we have discussed enough. It is the maximum height in millimeter of a flame that is produced in a lamp burning the petroleum fraction at standard conditions, which without causing smoking. So this is important because kerosene flame, if it smokes, that means it has aromatics, and that is why actually you would see that a candle which has made of paraffin wax, it doesn't smoke because you can't see a smoky flame from a good paraffin wax candle. Similarly, freezing point is the temperature at which solid crystals get formed on cooling. So you have a clear liquid, and then actually as you start cooling, it becomes slightly hazy. That haziness, the onset of haziness is declared as a freezing point. And this property is extremely important in jet fuel, as I already discussed. Minimum specification is either minus 47 or minus 52. So some of them are quite important variables for a certain fraction, like flash point is a very important variable for diesel specification. In our country, it is 35, but worldwide it is 62 because we don't want very light material present in the diesel. Similarly, pour point is a very important parameter for lubricating oils because lube oil pour point we normally keep at minus 16 or minus 12 degrees centigrade. In our country, we keep it at minus 6 actually. We don't go below minus 6 because that's okay because of the ambient temperatures are higher. Similarly, smoke point is more applicable to kerosene. Freezing point, again, for jet fuel. And of course, freezing point is also important for lubricating oil. Cloud point is very close to freezing point, the temperature at which its solid paraffin content begins to solidify, making the fraction cloudy. So they are very close, freezing point and cloud point. Cetane index is defined for diesel range materials. This is actually a percentage of cetane in a blend of cetane and alpha methyl naphthalene. So alpha methyl naphthalene has cetane number of 0, while cetane has a cetane number of 100. And a mixture of these two actually gives you the calibration mixtures from 0 to 100. And then you run that in a cetane number engine. So these are actually engines which are available from a company called CFR. This is Combustion Fuel Research. And this company is the monopoly in the world. There's a company in the US called CFR, which actually makes these engines. And then you actually put your sample in that engine. And based on the calibration that you had done from 100 cetane to 0 cetane, the machine will calculate will tell you the cetane number or cetane index is actually a calculated variable, while cetane number is actually a measured variable. Okay. Aniline point we have discussed. It's the lowest temperature at which a petroleum fraction is completely miscible with equal volume of aniline. So these are some of the characteristics or properties of hydrocarbon fractions. And I will just run you very quickly through what I have been saying, that some of the properties of petroleum fractions can be calculated if I know two properties. Like for example, if I want to find out the molecular weight of a petroleum fraction, the moment I know MEABP and specific gravity, I can calculate using this equation. And believe me, these equations are used in simulators. But actually, if suppose the petroleum fraction is heavy, then as long as I know the viscosity at two temperatures, that is at 100 degrees Fahrenheit and 210 degrees Fahrenheit, and the density and the specific gravity, I can calculate the molecular weight. In case actually for very heavy petroleum fractions, you cannot actually determine the mean average boiling point. Like for example, things like short residue, because that we cannot go beyond 560. So maybe 600 is the max we can go. So we cannot calculate the mean average boiling point here, but I can determine viscosities at two temperatures, and using that I can calculate molecular weight. Similarly, flash point. So flash point is related to the T10% point of ASTM D86 or ASTM D1160, and so basically. The lower the T10, the lower is the flash point. Okay, and so basically it is the slope is roughly half, 0.68. So please remember this, that any temperature, any T10 temperature if you have, you can calculate the flash point immediately using this equation. But overall, you need to remember that if my T10% is low, that means the flash point must be low. Similarly, the smoke point of a petroleum fraction is a function of Watson K or EOPK and mean average boiling point. Similarly, the cloud point again, can be calculated from these equations. In fact, properties like cloud point, yeah, they are a bit dicey, because they are more to do with the paraffinic content, and to some extent we can grab the paraffinicity using specific gravity and mean average boiling point. But you have to take it with a pinch of salt, the values of Cp given by this equation. But to get a fairly good idea to begin with, I mean, if you don't have any numbers, at least this will give you some number to look at. But of course, these things need experimental verification, particularly the cloud point and the freezing point, and similarly the pour point. So here you have, since it's a heavy material, pour points are generally for heavy material. You have viscosity at kinematic viscosity at 100 degrees Fahrenheit, which gets plugged into this equation. And aniline point, of course, aniline point, you can see that the higher the UOPK, that means the more paraffin it is, the higher is the aniline point, and vice versa. In fact, some of these properties are extremely important, because not many labs can actually determine thermal conductivity of liquids. And here we can have any petroleum fraction. There is no way in the world that you can determine thermal conductivity of any petroleum fraction, whatever you actually produce in a refinery. So these equations become very handy. Mean average boiling point, so this will give you the value of thermal conductivity at any temperature, provided you know the mean average boiling point of that particular fraction. Similarly, the cetane index is actually, as I told you, is a calculated variable, and it is given by the function of API gravity and mean average boiling point. But if you are actually adding a cetane improver, for example, there are cetane improvers called additives, cetane additives. If you add that to diesel, then these equations are not valid. Okay? In that case, then you have to actually go with the cetane engine to determine the CI value. So please remember that cetane index is only for virgin materials that is coming out from the crude oil in the diesel range. And if suppose you add something to improve the cetane, then this equation cannot be used. It has to be, the cetane number has to be done on an actual engine. Okay, and similarly, the critical temperatures, which these are the critical temperature, critical pressure, critical volume, eccentricity factors. These are the variables that you need to actually calculate to determine the vapor liquid equilibrium using equations of state, like Wicke-Virial equation of state or Peng-Robinson equation of state, etc. So this is critical temperature, which is again a function of specific gravity and the boiling point. similarly critical volume, and I did not put the critical pressure and the eccentricity factor, but the values are also there. So finally, actually, there's a small home assignment that I would like you to do by Tuesday, 5 o'clock. And please submit this to Mr. Jana, Bijoy Jana, and I'll explain what you have to do. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I think these two are same, so don't bother. This is one and the same. That is, vacuum HSD. HSD stands for high speed diesel. In our country, we don't call diesel as diesel. We call it as HSD, high speed diesel. I think this name has stuck because of historical reasons. So it is called vacuum high-speed diesel, and this is PWD stands for pressable waxy distillate. These are the nomenclatures used in our northeast refineries, where they can actually produce paraffin wax from vacuum gas oils. And this is vacuum residue. This distillation curve is, of course, using a simulator. You cannot determine this experimentally. So this is the data that I'm giving you. So we have 1, 2, 3, 4, 5, 6, 7, 8 fractions of a particular crude oil. This is essentially Assam crude oil, and these are the densities in kg per meter cube. So this is like zero point 0.8 is the specific gravity in gram per milliliter, and then you have volume percent distilled from IBP to MBP. And I will upload this lecture today. So whatever correlations that I have actually explained, you need to use this to actually calculate volume average boiling point and all average boiling points. So you have all the equations that you can use. You can program the whole thing on a spreadsheet and submit the spreadsheet if you like to Mr. Bera, and he can then forward it to me. Then the Watson K that can be derived from whatever data I have given. And then using this to calculate the molecular weight, the flash point, cloud point, and pore point using the equation that I have given. So if you can submit this by Tuesday evening, please do that. And this